of great minds. It is my pleasure to be able to introduce our next speaker today. As many of you are aware, Linux containers provide the ability to reliably deploy thousands of applications or application instances in seconds. But you might ask, how do we manage it all? Well, Kelsey Hightower is about to help us answer that very question. Kelsey is a product manager and chief advocate at CoreOS. He has worn every hat possible throughout his career in technology and enjoys leadership roles focused on making things happen and shipping software. Kelsey is a strong open source advocate focused on building simple tools that make people smile, which I like very much. When he is not slinging Go code, you can catch him giving technical workshops covering anything from programming to system administration and his favorite Linux distributions. Please join me in welcoming Kelsey Hightower.
Hello. I am excited about the tech I'm going to show you guys today. So I'm going to be talking about managing containers at scale with CoreOS and Kubernetes. There was a bunch of Kubernetes talks today. So I'm going to skip over some of the high-level stuff. Hopefully you guys got a lot of the high-level stuff in the other talks. I'm going to try to give us some examples of like how I run things. But before we get started, we have to talk about containers. Now, a lot of people, when they approach containers for the first time, this is the vision you have in your mind, right? You're going to take all of that technical debt that you've incurred over the years, and you're going to just package it up in containers, and your life's just going to be awesome, right? You know, you got this working on your laptop, it looks wonderful. You show your family members, and they're like, what is that? So then comes the big day, right? You actually have to get it to work in production. Now, it's not as bad as it seems. You know, right? All things have issues. You know, you may lose a few containers, but it's okay. Most of the runtime engines will bring back your containers. And now that you're in production, the next phenomenon happens, right? You actually have to take real traffic from customers, right? And that's when it gets real interesting. Things don't go the way as planned, right? So then you call in ops for the first time. And ops comes on and says, all right, what are you doing? It's like, well, we're using containers now, and everything is awesome, but we have a small problem. And the good thing is, though, most ops teams are designed to come help bail you out. Right? This is kind of like where ops exists in a lot of cases. But the bad news is that they can't help you on this one. You're pretty much on your own. Because a lot of times, I think people start out with containers with a bad pattern. Right? They start up trying to take their existing tools and retrofit them to work with containers. And in some cases, that can actually work for you. So now that you're on fire in production, you know, the next set of bad news is that your entire family is disappointed at you, right? You told them containers were going to be the thing that got you home on time. But no, containers. So you can end up there, right? And it's not all that bad. So what do we do now, right? There's tons of things we can do. When you guys see this particular slide, that means I'm going to try to do a live demo. If the networking is working correctly, this should be smooth. If not, just laugh. So the first thing we need to do is set up a slightly better infrastructure. So we need a better foundation here. I'm using a tool called Terraform. Has anyone heard of Terraform before? Awesome. Terraform is a very awesome tool because it allows you to declare your infrastructure like you saw in the earlier demos with Kubernetes, right? You declare your application state. But it would be nice if we could declare our infrastructure as well. So the way we declare our infrastructure with Terraform is we have some config files. One of them is our main config. And here I write a bit of code. Here I'm saying, when this is all finished, I want you to spit out the API server that I can use for Kubernetes. And then a couple of template files. And then we go down here and doing everything on GCE, but I'm not using their container service. I'm trying to mimic what you would do in your own environments or in a different particular cloud provider. Here I'm setting up etcd, and we'll talk about etcd later. I'm saying that I want 3 of those, and Terraform provides a bunch of primitives that I can actually use this data in other parts of my infrastructure. So what Terraform can do for us is set up a complete cluster. And what the cluster looks like right now, and I have to set up before that here, it looks like this. So I have this many nodes, And the nice thing about Terraform is you can run it multiple times, and ideally, it shouldn't break anything. So what it's doing is inspecting my desired state and making sure that my infrastructure is that way. So right now we have 3 worker nodes in this set. And what I want is a couple of more. So let's do this now. And so what I'll do, I actually have a lot of things in variables, so that way I don't have to touch my main config. I'm going to increase one of my variables. So I have things like my SSH key, what zone I'm going to be in. The only thing I'm concerned about right now is my worker count. So I'm going to go ahead and increase that worker count from 3 to 5. And we'll see what Terraform does with that. So now I've changed I declared that I want a different type of infrastructure than what we have. So the nice thing about Terraform is that you can actually plan things out. So it inspects our state and says, hey, there's things missing. So we kind of get a diff of our infrastructure, right? You're missing these 2 servers in your infrastructure. So now that we have this plan, we can go ahead and apply the plan, right? So you can check these things in and apply them when you're ready. So now we do the application, and what happens is Terraform goes out and calls all the right APIs to bootstrap those servers, and then those servers will actually get all the Kubernetes components installed and be ready to become workers in my cluster. So now that's going. If we check out our console here, we should see the 2 new servers being spun up. And it's basically my count variable incrementing the node names. So now we have this new infrastructure going. But before we get there, we need to talk about the individual components that go into that infrastructure. So the place we start is, most people are doing this today, or at least understand the idea of containerization. And in the CoreOS world, we start by containerizing everything, right? And we'll talk about the impacts of that. And then for us, we also like this idea of a self-updating operating system, right? Because all of these new technologies come out, you kind of want the new bits to allow you to actually utilize all those things when they actually ship. There's also some security bits there. Like when these security vulnerabilities hit, you want your machines to have the patches applied so you're not vulnerable in production. And then the next thing is first-class tools for actually doing some of this distributed computing stuff. So a lot of components we build at CoreOS are around enabling these ideas. Now, when we stitch everything together, things are really easy with one node, but what we want is a cluster. So we tie together those things with various tools that we're about to introduce, and each of our hosts looks something like this. They're very minimal operating systems designed to run containers specifically. There's no package manager on a CoreOS system. There's actually no easy way to run Puppet, Chef, or Ansible because we don't ship Python or anything like that. If you wanted to use a tool like that, you have to bring it in a container. And there's patterns to show you how to do that. But overall, our systems are designed to come up and start talking to each other immediately. Now, application containers. And to me, I like the term application containers because it really clearly defines what you're doing here. Containers have been around for a long time. People use them in different ways. Some people use containers like system containers, where you treat a container like a virtual machine. But what we're talking about here are application containers. And to understand application containers, think about what you do normally in a typical Linux distro. On the right, that's your application, right? So, maybe you're writing a Java app or a Python app. That's your source code and maybe some definition of the libraries that you want. On the left side is usually what an operating system provides to you today, or a distro, to be more correct. You're going to get your thing like your kernel and various runtimes. And what they try to do is be helpful and give you specific versions of those runtimes, so that way you can rely on them and count on them based on the operating system version that you're dealing with. But that makes things really hard. What happens when your app wants to have 2 versions of the app installed at the same time with different versions of those runtimes? That's when it gets really, really tricky. And then people revert to tactics like one application of a virtual machine, right? And to me, I really think virtualization caught on big time, especially in the Unix space, for this very use case of having the dependency conflict be isolated at the VM boundary. So what we do in CoreOS is we move that line, right? We change the contract between your application and our distribution. We say we're no longer going to provide any of these runtimes or extra software. We're going to push that out to you to make that decision. Now, for developers, this means that you get to choose what runtime and what runtime version and the dependencies of that runtime with your app. You have to put it in a container. So inside of that container, not only are you going to include your source code, you're going to include that runtime that your source code requires to actually execute. And the same goes for other components. And once we establish that contract between you and the application, we can do things like update the operating system now. So in CoreOS, by default, you can't install any new software under the system path user or under bin. Those things are actually read-only when we boot up. So a CoreOS system has two partitions. And the first partition is your first install, right? So whatever version of CoreOS you start with. And then in the background, we check for updates. And this is a very similar process to what the Google Chrome browser introduced to the world many years ago, where it would just update and check for updates and apply those updates behind the scenes. Now, if that update checks out, we can reboot the system to apply, right? And in some cases, you don't have to reboot the system for all updates, but when it comes to things like systemd, maybe a new kernel, if you're not using like ksplice, you have to reboot the system to be sure that you're in a known state. So these are atomic updates, right? Now, if that update doesn't apply, we can go back to a version that went before, right? So this kind of gives you a very clean thing that you can count on because the OS is very small and is very isolated. Now, during these updates, we don't touch your containers, right? Those live in a different path, different partition, and that data is yours. Now, we try to have people and encourage people to keep up with the runtimes that they're running. You know, hopefully today there's really not a lot of incompatibility between your application and the kernel that you're running on, since it's a shared kernel. But maybe over time that might become a problem. So that's something to be aware of. Now, once we have a bunch of these systems on the network, we need to be able to connect them together. Right? We need a way for them to agree on things like IP addresses and database passwords. And the way we do that is with etcd. So etcd is a highly available key value store for shared configuration and service discovery. All right, so what does that mean? So in a simple case, it's a very simple key value store, right? You have things like, here's a couple of services, and the actual app that will be setting those keys or your applications that you boot up, and they just register themselves and say, hey, a new container started, and I live at this particular IP address, right? So my first database container comes up and tosses it IP against it. The second one does the same thing. Now, if you want to know where all the databases are, you can get a query and say, hey, ask for a specific database, or iterate through all those keys, and we call that service discovery. Right? So when you're running all of these containers, it's really easy to lose track of them. Right? So then you implement something like service discovery. This is a very common pattern that you see in these type of systems. Shared configuration is the other primary use case for etcd. And shared configuration, like I said, in our systems, these are larger clusters, and we want convergence quickly, right? And configuration management tools do a really good job in most cases. But if I give you 100,000 servers, and we have to wait until those configs propagate, that may take too long for some people. So you want a system that, you know, we can all watch for configuration changes and kind of get this real-time feel for updates. So in Kubernetes, you guys may have saw this in earlier talks, like a pod, when you create one of these manifests, it gets stored in etcd. So etcd is currently the backend for Kubernetes. So all those definitions that you write, those cluster configs, they go into the Kubernetes API, and they get stored in etcd. And this is important to store these in a thing that has consistency guarantees that will work for a distributed system. And we touched on service discovery. And we'll see later on how service discovery works in Kubernetes and how they expose it. We saw a very raw implementation of service discovery where your applications need to know about etcd, they need to know about keys, and they need to know about the key layout. That's too complex. And there's better ways of doing this with a little bit of abstraction. And locking. So now that we have all of these servers that can update themselves and communicate, one thing that could be tragic is if we have 1,000 servers and they just start rebooting themselves at the same time. That can cause a full system outage. So one use case that we do with etcd is we have a tool called Locksmith. And what Locksmith does is the reboot manager for CoreOS, right? So it's backed by etcd, meaning each of the servers has an application called Update Engine on it. And what Update Engine does is the thing that runs in the background, and it checks for new versions of the operating system. When one is found, it's pulled down to the server, verified, and installed into the second partition. Once it's there, we can start to coordinate who should reboot first. And we do this by obtaining a locking etcd, which is a fancy way of saying is we have a key that we agree on, and we all try to grab that key and write a value in it. And then we have a TTL to say, this key is mine for, I don't know, about the average time it takes for me to reboot. And as long as you have a lock on that key, if the other servers are respecting the lock, they won't reboot. They'll just keep trying until that lock is free. So once you have the lock, you're free to reboot yourself, come up, and release the lock. If you never return, the TTL will expire on that key, and the other servers can take their turn rebooting. So when you think about locksmith, it's the semaphore for reboots, right? You want to control access to that particular resource, mainly rebooting the servers in your cluster. And then you get a couple of tunables, right? So if you have thousands of servers and they reboot really fast, it might be okay to do one by one. But if you have bare metal systems, like, I don't know, 64 gigs of RAM, 128 gigs of RAM, how many people know how long it takes to reboot a server 128 gigs of RAM? A real server. Like most people are used to the cloud these days. But a real server, when it comes up and does a full boot process, it scans all of its memory. And today, that's a sequential scan. On average, 20 minutes to reboot a server or a lot of memory. So rebooting one by one may not be the strategy you want to do. You may prefer a different strategy. Mainly, some of them like, hey, just reboot whenever you get your update. Or, best effort, try, maybe if there's less than 5 rebooting at the same time, sure, I'll try it. All that's configurable and tunable, and you can kind of write your own. Locksmith CTL is the tool that you use to write your own, right? Make your own strategy. Maybe there's more heuristics you need to determine before you reboot. If you're a database server, maybe you want to flush connections or switch to being a slave instead of a master. There's other things you can do there. The next thing we need once we have all of these systems is networking for containers. Now, this is the first shop that most people run into when they adopt containers for the first time. It works great on a single host. You spin things up. You know how to get to them. You add in another host. And by default, the most popular container runtime engine is Docker. And Docker has dedicated bridges on each machine that aren't really coordinated. So we built Flannel to help coordinate that network setup, right? And it's also required by the Kubernetes model. The Kubernetes model specifies that every host within the cluster, all the containers should be able to talk to all the other containers. And all of those containers should be able to talk to every host. Now, one way of doing that is with an overlay network, right? If you run on a cloud platform, they won't give you access to layer 2 networking, right? So that means things like DHCP won't work. You can't just fire up a container and get a DHCP address. They block that. So what we got to do is kind of create this meta network on top, usually an overlay. And Flannel is actually configurable, so it has multiple backends. You can choose how you want to do this overlay. Now, one slow but easy way is to do UDP. Not very optimal. It has VXLAN support, which is preferred. Has the least amount of overhead when you're doing this stuff. But if you're running on a cloud provider that allows you to manipulate their global router, kind of like the way GCE works, those providers give you access to your own routing table in your virtual network. So then Flannel can run in a mode where all it does is like allocate these subnets for each of those Docker bridges running on each system. And then it can just programmatically update these routes and then deal with L3 routing. So when a container wants to talk to another container on the server, it just goes to the routing table like normal, right? And that gives you the best performance. And here's what it looks like at a high level. You have 2 systems, and ooh, there's a laser pointer on this thing. Like, woo, lasers. Lasers are cool. So here's what you get by default. When you bring up a machine, Docker creates this bridge, and it picks a random subnet range, right? And it says, all right, I'm going to pick this range. And what it starts doing is this first IP here, that's for Docker. And then just incrementally starts giving each container that starts up an IP from this range. Now, Flannel takes advantage of that fact. And what we do is we inject, we start Flannel, and we build this overlay network where we can encapsulate packets that come out if you chose encapsulation. And then we can configure Docker to have the IP range that we want Docker to have. So we can coordinate all of that by having etcds somewhere here in the cloud. All of these final instances go to etcd and say, hey, etcd, what large range do we have? And you start out with maybe a /10. We can carve that up into smaller subnets and give each host a range in that subnet. So these two things are in the same subnet, right? And then what happens now is any container that wants to talk to another container, if we need to do any encapsulation, it comes out of Docker, hits Flannel, we do the encapsulation here, and then we send it to the next hop, and then we can de-encapsulate and get you back to the next container. So this allows this to work in pretty much any environment. And this is very common in the VMware stack. So this is what's happening if you're running a large VMware cluster. They use VXLAN to give you that virtual network. Now, our revenge, right? We failed horribly our first time around by hand-rolling a container solution. And Kubernetes comes on the scene, and it takes a lot of ideas from the past. You probably saw this in some of the other talks. A lot of the things that you see in Kubernetes, the Google team has been experiencing. There was a board white paper that came out recently. If you haven't read it, you should check it out. It definitely goes through some of the challenges of running a system like this, some of the things that they've learned over time, and what they hope to improve in this open source project called Kubernetes. One little bit of trivia here. If you ever see Kubernetes K8s, how many people know what that is if you don't work at Red Hat? Do not raise your hand, Red Hat people. What is it? Yeah, like why? What is K8s? Yeah, exactly. Like when I figured it out for the first time, I was like, ooh, I get it. 8 letters between the S. You get K8s, right? So Kubernetes is an open source orchestration system for containers. It's API driven and declarative. And that's the most important part about this. It's declarative, just like what we saw with Terraform. We don't write a bunch of scripts. We don't write configuration management code and tell things to do things. We basically say what we desire, give things like a count, and we expect the tooling inside of the Kubernetes cluster to do the work for us. And it also gives us a better abstraction around service discovery. And to me, this is one of the more powerful features using a system that they call labels. It also does monitoring if your containers or pods conform to some of the specs on what Kubernetes can do. So with that, we're going to attempt to do a live demo of Kubernetes. And hopefully it doesn't overlap too much with what you guys saw earlier. And if it does, I'm just going to do it anyway. How you do it. All right, so we got those servers, and we got Terraform going. So now, one thing that happens in Terraform, let's just do this apply again. Once we have our infrastructure booted, I'm telling Terraform to give me back the API server at GCE. So what I'm doing is using the secure port of Kubernetes. I have the IP address and port. And what I did behind the scenes in Terraform, I actually uploaded tokens securely. So authentication tokens that I can use to actually interact with this thing. If I've done that wrong, that means you can take your laptop right now and start interacting with my cluster. Please don't do that. That'll probably be sad. So what we can do now is once we have an IP address, we can use the kubectl tool to actually say, you know what, I want to start interacting with that cluster. Now, the kubectl tool is the primary thing you would interact with the cluster on the command line. It basically just makes it easy for you to work with the APIs. So with that one command, I basically updated one of my cluster configs. I would show it to you, but I have like an API key in there, and that would be bad. So I'll skip that part. But now that we're configured to talk to our newly minted cluster, we can start running commands here. So right now I'm going to get the number of nodes in my cluster. And earlier I registered these 3 nodes, right? If I wanted to register new nodes, I can do kubectl create -f nodes, and which ones don't I have in there? So testing 3. So that should make an API call. And what happens here is I'm sending this particular configuration to the cluster. So I'm saying I have this new node object. Its name is named after basically this naming convention that you get from Google's internal. And here's the XR ID. Some people like to use IPs, but I really like the NS name. It makes it easier to reason about. So once that's done, I should list nodes again and have another node. Now I've written tools that automate this process for you. A lot of the cloud providers can also automate this process when it spins things up. But it's really nice to have these two steps, especially if you're dealing with smaller environments that need more checks and balances. Maybe you release the server to production and it needs to go through a burn-in process first and you want approval before it goes in. So you can kind of build your own pipeline before you add these nodes. Then once we add nodes, the system that I'm going to demo today is I have a little application. And what this application does is it talks to Postgres and it tells you all the features that Postgres supports. This app is called PGView. And what we're going to do with PGView is the first thing we need is a Postgres database. So the way you create Postgres, pods is you give it a specification. So here's a specification for my Postgres pod. And you guys may have seen some of this in the earlier demos. But I'm being very specific here. I'm saying I want a pod. And a pod is one or more containers that get scheduled as an atomic unit. And the things that are important here are, number one, the labels. The labels allow us to do things with service discovery, and we'll see that. We can also talk about, where is my mouse? We also talk about volumes. So in this case, this is a database container. Now, the Red Hat guys are doing a lot of work on making volumes actually work with, let's say, remote storage options. Or if you're in the cloud, there's like persistent disk that you can move around. In this case, I'm using something simple, just the host data, the host volume that's on my current server. And then here, I'm specifying the container I want to use. I just want to use a Postgres container. It's going to come from a default place. And I'm doing something really bad here, setting the password on the fly. Don't do that. All right, so we add that database. And once you add your pod, you can start listing your pods. So we can do kubectl get pods. And we see all the pods. Now, the output there looks really, really, really crazy. And the thing that Kubernetes does support is you can actually give these things templates. So here's a template file and some Go magic that I'm doing to actually parse that up to be a little bit cleaner. So I'm going to use that going forward. So what we can do now is you can do, let's see, template. So what we want to do now is get a template file. And we're going to use that template file to list this out in a different format. Right? So that's a little easier to read, especially when we start adding a bunch of pods. All right, so now that we have that, we can actually start interacting with that database using that IP address if we're inside the cluster. But we don't want to have our applications connecting to the database directly on this pod IP because it could move in the future. So what we want to do is use a service. And a service looks another declaration. And we give one for Postgres. So here's what a service looks like. We basically are saying that we want to have Kubernetes dynamically allocate an IP for us, one that will actually live inside the cluster. We don't get bound to an interface, and if we have time, we'll look and see what the magic is. We want an IP address, and what I want you to do is allocate the IP address and have our proxy server, which runs on every machine, and we want you to proxy traffic for port 5432 to that IP address. And I want you to do this for all the pods that you find with a label called Postgres. Now, when we set up our pod, it had a label called Postgres. So we create this service. And once you create the service, we can get at the service. Oh, no service, so we'll create it. So kubectl create -f services Postgres. So what happens behind the scenes is Kubernetes allocates an IP from a pool that you give it. It's called your service portal. And it grabs that IP address, and it's ready to listen on every host in the cluster to be able to forward traffic to this database. So with that all set up, I'm able to now to deploy my application. Now, my application is going to need to know how to get to that database. And this is where service discovery comes in. Now, for every pod that I launch, so PGView is written in Go, you can ignore much of this source code, but we're just going to go down to where we actually make that database connection. There's a faster way of doing this. So down here in my main function, here, before we actually connect to Postgres down here, I want the actual IP address and port, right? So what happens with Kubernetes, all those things that are services, they follow this convention. The name of the service, underscore service host, underscore service port. These are injected at deploy time into all of your pods that come up. So you can use this as a form of service discovery. And remember, the service port and host here is the thing that's kind of is like your virtual IP. It's not actually typing in the pod. and then I can connect. So if this works, we'll be able to connect to Postgres. And I'm also going to need memcache in that same pod with my other app. So there's going to be two containers that are going to live in this pod. We're going to have memcache local. So anything I get from the database, I store in memcache. So let's deploy our application now. So we're going to use what they call a replication controller. You probably saw this earlier. And what we're going to do with the replication controller is we're going to ask it to deploy version 1.0 of our container PGB. So there's a bunch of containers here. Now we're going to give it a set of labels so we can do some service discovery here if we need it. And we're also going to have it also deploy memcache in the same pod with us. So that way we can address it on localhost. Now we're going to start out with 1. So what we'll do is we'll do kubectl. We're going to create this replication controller called pgview stable version 1. Now that's up, we can review all the pods. So I'm going to use my template again to make it a little easier to see. So right now it's not running. It's actually in the pending state. And it's actually pulling those from upstream. And it found an IP has already been allocated for it. So now it's just bringing in the containers that it needs. So now we're up and running, right? So I could also hit those pods at that IP address. But we're not going to do that. We're going to create a service really quick. So the same thing as before. We'll create a service for pgview. And this one, we only care about a few of the labels. So now that we've done that, we can actually look at our services here. So now I have the service IP for pgview. Now we can start connecting to our application. So I haven't opened any outside firewall rules. So what I have to do is log into one of our servers. So let's grab one of the servers that are here. We should be able to just pick one. And once we're on the server, log in, all right, we can interact with the service. Which one did I log into here? I actually copied some configs up to this one. All right, so we'll grab into that one. We don't want to be on our Kubernetes API server. All right, so now that we're here, I should see a couple of RPC files, and we do. So what we can do now is hit that service to see if it works. So first thing I'm going to do is just see what the version is. So we take that service IP, and what we're going to do is send it some data, basically an RPC call, and see if we get the version. Who knows why that's not working? Exactly. Exactly. Is that a Googler? That's a Googler in the background. I was counting on you to be here today. Without you, we would all be lost. Okay. All right, so now we're going to hit the service IP. That's when we get the version. And now let's see if Postgres works, right? Now this is where things like, if they're not going to work, this is where it's not going to work. If this works, you guys should cheer. All right, so I introduced a sleep here to make sure that the first query is expensive. There's a 10-second delay, and it works. And if memcache is working, this should be fast. And it is. Good. All right, so we're sweet. Now we're in the ball game. So what we're going to do now is we're just going to emulate what customers see. So what we're going to do is just have, just hit this every second. Can I write bash? Oh, I still know bash. Okay, good. So now our customers are hitting the cluster. So at this point, you're really excited. You got one node in production doing your work. So now it's time to scale things up. So now we can interact with the Kubernetes API to give us more nodes, right? So what do we have now? We currently have one pod running, memcache and pgview version 1. And now I want, 5 of them, right? So let's say we're going to resize that. So we resize it to 5, and we're going to do it to the stable controller. So we hit the button, and it says it's resized. Now when we look at this, we see the pods. And most of them are false, some of them are running because some of the pools have already happened. And we'll get a few. This is insane that I'm trying to do this on the live internet. But wow, the containers are actually being pulled, and they're done. So we go over here and we see what the customer's view is, and they're still getting 1.0. Things are working. And the way this is working is our service proxy is proxying that traffic and doing a load balance between all of the pods that show up. And we don't have to deal with the individual IPs of those pods, mainly because the service proxy is handling that for us. Now comes the adventurous part where you want to upgrade that cluster. The nice thing about this using these specifications is we can spin up another controller and implement what we call the canary pattern. So the idea with the canary pattern is we're going to spin up another replication controller that will be in charge for another set of pods with a different set of labels so they don't clash. And ideally, that replication controller will be responsible for a pod set that has a new version of the application. So let's do that now. So we'll do kubectl, and we're going to create another replication controller. And this is going to be the canary controller. And its job is to spin up a new version of that app. Now, something to keep in mind here is that the way the services work, I'm being very specific that I only care about a subset of the labels between the two of those pods made by those controllers. That means the service proxy will actually proxy traffic for both of them, even though they're different versions, right? So with that, we should see we have a couple of images running, and we're looking for a new one, 2.0. And now the 2.0 has been deployed, right? So what does that look like to the customer that's hitting their application? They're starting to see some 2.0 traffic, right? This is what we want. Now we'll run that for a while to make sure that developers haven't sabotaged this. And everything's checking out. No pages are going off. It's safe to go ahead and deploy 2.0 across the stack. So how do we do that? The way we do that is, in this case, I'm going to just use another replication controller. And that replication controller just says, you know what, just use this image instead of the other image. That's it. Basically looks the same, but the nice thing about these things, you can check them in and version them. So what we're going to do is use version 2 of this PG view controller to see what happens. So what we can do is, maybe I have it in my history. Yes, I do. So maybe you saw earlier this rolling update command, and this is going to orchestrate these APIs for us. So what I'm going to do here is say, every 3 seconds, what I want you to do is, I want you to update, or basically replace that existing controller with this other controller. And we run this, and now Kubernetes starts to do its work behind the scenes. We kill some, we add some. We kill some, we add some. And this will do this for 3 seconds, going and going and going. And as this is happening, what does the customer see? Well, let's see what we get here. Looks like we still have the same number of 2.0 pods, and we should see the frequency of the 2.0 pods start to increase here. If things are actually working. They better work. Let's check on the actual pod status here. All right, there's a few of them are going through. Do we see the 2.0 frequency increasing here? I think so, yeah, we are. Things are increasing. So the cluster is rolling, and we're starting to get convergence on this new specification that we defined. Our replication controllers are working in tandem to do it. And soon here, what we should see is 2.0 across the board. So let's check on our... Are we there yet? Yeah, we got it. So we've just updated all the machines in the cluster, and we no longer need that canary controller. So what we can do there is we can destroy that replication controller. Let's get the name. So let's get the replication controllers, and we can destroy one of them. We're going to destroy the canary controller, PG view canary, and we want to cascade that because we want it to take all the pods with it that it's managing. Oh, I got to spell it right? Oh, I'm thinking about Terraform here. There we go. So what will happen now is that we're going to delete that particular replication controller. And since we added the cascade option, any pods that it was managing go away, right? So it's really easy for the operations person to declare what they want. Developers get to push what they want, and we actually get to manage the cluster in the very same way. And with that, that's the end of the presentation. Thank you.